So Dr. Hongjie is the founder and the CEO of Reexen. I will leave it to her to introduce what Reexen does. So her presentation today is making the signal chain more intelligent and efficient with analog digital acceleration. Thank you.
Thanks. Hi, everyone. My name is Hongjie Liu, founder and chairman of Reexen Technology. Reexen is a company doing analog digital acceleration and trying to make the signal chain more intelligent and efficient, suitable for ubiquitous AI. Here's a brief introduction about Reexen Technology. We were founded in 2018 and got 3 series round already of investment. We are located in Shenzhen, Chengdu, Shanghai, and Zurich. So right now we have already 60 people, 70% R&D, and including 3 young scientists from global leading research institutions such as ETH-Zurich, Nanyang Technological University, and Imperial College London, actually. We have already mass-produced our first chip that is audio processing, ultra-low power audio processing chip with analog signal processing and InMemory Computing inside. Our second chip, ADA 200 for vision processing, is also already back from the foundry. We are testing it. Hopefully we can provide demos next month for our potential customers. So the team of Reexen comes from different top universities and also top companies. We have already more than 30 patents granted. Our team also published more than 10 ISSCC and GSSC. So our co-founding team comes from ETH-Zurich with a research background of neuromorphic engineering. We did our PhD with Prof. Toby Delbrook, who is the inventor of event-based vision sensor, also a pioneer of neuromorphic computing. We collaborated with Sony, Samsung, and IBM, and later we founded our own company focusing on neuromorphic analog signal processing and in-memory computing. The huge number of sensors generating data demands more efficient processing chips. So especially in the area of wearable smart home and also IoT devices. But traditional signal chain is not that efficient for machine learning purpose. It's good for human to visualize or to hear, but it's not good for machine vision and machine hearing. Traditionally, the sensors transfer physical signals to electric signals, and then all the raw data, normally all the raw data are converted from analog to digital, and then most of the signal processing part is done in the digital domain. However, the digitization process is very power consuming, as we all know that the analog to digital conversion, the power and the area consumption of the AD converters rises as the sampling speed and also the sampling resolution rises. So in normal sensors, for example, CMOS image sensors or audio sensors, more than 70% of the power consumption comes from the AD conversion. So the ADC is the speed and accuracy bottleneck for the whole signal chain. And secondly, to do most of the processing in the digital domain after digitization, is also not so efficient because we need to do all the because the digital computing is not always more efficient than analog computing. Moreover, the traditional digital signal processing architecture is phono-in-one architecture. It separates the computing unit and the memory unit. More than 70% of power consumption and latency comes from data transfer between the memory and computing unit. And Moore's law also also has slowed down. And so the performance of the digital chips cannot increase as fast as previously anymore. So Reexen's approach is to integrate analog pre-processing and in-memory computing in one chip, and also in this sense we can improve the efficiency of the whole signal chain. Firstly, to do analog signal processing before the digitization can reduce the requirement, the speed and resolution requirement of the ADC, and hence reduce the power consumption and area of it. And also analog signal processing itself and some resolution requirement is more efficient than digital computing. But analog signal processing is not perfect because of the mismatches and the non-linearity issue. So for more high-level computing, we use mixed signal in-memory computing to do the implementation. Analog AI cores will the trend of analog computing is also valued by big companies such as IBM. Here is a graph. On the left is a graph showing the area and power consumption of between analog and digital circuits. So below 60 dB SNR, analog circuit will use less area and power to do the same computation. And also 8-bit resolution is normally enough for most of the edge applications. So that's why we are coming back to analog processing again. And in-memory the second approach is in-memory computing. Aside for high-level computing, it's not good to use pure analog, and then we use mixed signal in-memory computing. So between layers, it's a digital connection, but inside each layer computing is analog circuit, and in-memory computing also reduces the latency and power consumption between the computing unit and the memory unit. As this shows the energy cost on the bottom, it shows the level of energy cost comparison between the multiplication and also the computing the transfer cost between the computing unit and different type of storage. So on-chip storage, on-chip communication is more efficient than off-chip DRAM computation, and that's why people the digital world are focusing more on in-memory computing. However, if we can integrate the memory and computing together in one cell, that will be the most efficient. Both academia and industry has been researching on in-memory computing based on different type of memory. Flash, DRAM, non-volatile memory, including RAM, MRAM, or phase change memory, and also like volatile memory such as DRAM and SRAM. So all of those different approaches have pros and cons. For example, for flash, for storage is really high density, but the speed of computing will be much lower than comparing that of SRAM-based in-memory computing. And for DRAM-based in-memory computing, it's not most of the approaches are near-memory computing, not really in-memory computing, and also it's difficult. For scaling the technology. The speed is relatively low as well, comparing to SRAM. So for memory computing based on RAM and MRAM, because so I don't know, like we hope RAM can one RAM cell can represent multiple bit cell, but the truth is for current mass productive technology, it's not yet very high bit resolution yet. For TSMC, from TSMC, the mass productive technology is still 1 bit RAM. So in this sense, I think RAM based in memory computing, the maturity will come after 5 years. For SRAM based in memory computing, there are two different approaches. So TSMC and some other institutes has published one paper on pure digital SRAM based in memory computing. It's easier to get a high bit resolution if we use pure digital computation in memory based in memory computing. However, the area and the power efficiency is much lower than comparing to SRAM mixed signal SRAM based in memory computing. And within mixed signal in memory computing based on SRAM, there are also different approaches. So some use the memory cell from provided by the foundry. But we at Reexen, we don't use that. We build our own in-memory computing cell from logic transistors, and we can do in-memory computing with only 6 transistors without adding more transistors. Moreover, our approach is also more robust to process voltage temperature variation, and also we offer one-to-one mapping between numerical and physical computation. And thanks to the feature of SRAM and our logic-based SRAM, we can offer unlimited number of write cycles. The speed is also much higher than comparing to non-volatile memories. And most importantly, it's suitable for all the processes. But of course, it also has some drawbacks. For them, the relatively high leakage and also relatively low storage density. However, talking about computing power, we can offer much higher speed, like several orders higher than flash. So in the end, our computing efficiency, area efficiency is higher than other approach. And so, as I said, we can offer one-to-one mapping of 8-bit by 8-bit multiplication. So this is much better than previously published approach, where they normally don't have one-to-one mapping of this 8-bit multiplication. Although they designed the circuit to work for 8-bit resolution, but it's nominal, it's not effective 8-bit. However, Reexen's approach can offer 8-bit effective resolution. Talking about the efficiency, we compare our result with Samsung with papers published by Samsung on digital neural network processors. So at 22 nanometer, we can offer 300 gigaops per millimeter square and also 20 teraops per watt for 8-bit by 8-bit multiplication, multiply and accumulation. Meanwhile, Samsung's digital approach offers a similar area efficiency at 8 nanometer. As we all know, if we shrink the technology, the area efficiency will increase, and that means Reexen's technology is more area efficient than the digital implementation. In terms of power efficiency, we achieve higher efficiency even than Samsung's 5 nanometer implementation. So to conclude, Reexen integrates, we insert computation at different levels in the whole signal chain. We do part of the low-level computation before the digitization in analog domain, and then we do higher level computation using using CRM after the digitization. But of course, our CRM is also mixed signal. It's not that as we do it after the digitization, it's pure digital. It's that it's all mixed signal. So within the CRM, there are also a lot of ADDA converters, but still it's more efficient than pure digital implementation. For our product line, we already have our ADA 100 mass produced, ADA 200 back, and ADA 300 in development. So in general, comparing to digital implementations, we can offer 1/3 cost and 1/10 of the power consumption for same performance. That's all of my talk. If the audience want to collaborate, you can scan our QR code for collaboration or write an email to info@reexen.com. Thanks a lot.
Okay, thank you, Dr. Hongjie. So can you share an analog AI use case with our audience? I think some of us are still new to analog AI.
Let's take analog signal. Let's take audio processing, for example. Normally, for example, for keyword spotting, people do some sort of pre-processing before feeding the features into neural networks. The pre-processing normally includes like filter banks or MFCC. So we at Reexen we implement the filter banks before ADC in the analog domain. That's an example of analog signal processing. And also another one, as I said, we did our PhD in the institute where dynamic variance sensor was invented. So dynamic variance sensor is also a type of analog signal processing because the variance sensor has analog signal pre-processing in each pixel cell before digitization. That signal processing what that signal processing does is to extract the temporal difference at each pixel of the illuminance. Yeah, that's another example. Thank you.
Okay. So another question on the last slide, you mentioned compared to digital, we're achieving 1/3 and 1/10 of power enhancement. So what digital architecture did you use in the benchmark?
Yeah, actually we compared with the most efficient available chips sold on the market. Yeah. So I don't know whether it's good to mention the name of the company, but yeah, because we are a company, we're not doing research. So normally we compare our product to products from the company that has really like not a very small volume sales. So we compare to that one. Yeah.
Okay. So next question on area and the power comparison. How does it, what's the dependency on the technology node? Does it get better or worse with more advanced technical nodes?
Yeah, actually comparing pure analog to pure digital, if the technology node shrinks, the benefit of analog will drop. However, if we talk about mixed signal, then it really depends on how we design the architecture and so on. Yeah.
Okay. Another question from the audience. Can your technology be fabbed using FinFET technology? How will common analog variations affect chip performance, such as mismatch, offset, etc.?
Yeah, it can be migrated to FinFET technology, and we are planning it. In terms of mismatch and offset, this kind of non-ideality of analog signal processing, as I said, we don't do analog signal processing to achieve very high resolution, for example, 32-bit or 64-bit, because it will require very large area and energy to do that. And as one of my slides shows, so yeah. So if we want to do, if some of your application really needs very high accuracy resolution, then it's not good to use pure analog, and that's why we divide our computing into analog and mixed signal. And mixed signal will offer better resolution than pure analog at fixed cost. Also, we can also implement some part of the computation in pure digital if it really needs resolution, for example, higher than 16-bit or 32-bit. And also, so when I talk about resolution, I'm talking about the effective resolution we get already having considered the mismatch and offsets. Yeah.
Okay, so one attendee is asking, do you offer any test chip for evaluation?
Yeah, so we offer test chip after signing NDAs and also after evaluated the portfolio of the collaborators. Yeah, so please write an email to or scan our collaboration WeChat for discussion. Yeah.
Yeah. Next question.
Can I ask?
Oh, yeah. Do you mind hold on for a second?
Yeah, sure.
Yeah,
sure.
Yeah, I will let you. I will make sure you have a chance to ask your questions. Yeah, let's address the question from the audience first. Are there any size restrictions on the analog cores? For example, maximum dimensions of matrix vector multiply supported in one core?
I think the audience who asked this question wants to ask about the maximum size of the mixed signal in-memory computing part. As I said, we build our mixed signal in-memory computing core from a normal logic transistor. So there's no strict maximum size. You can think about if you build a CPU or GPU core, and of course it cannot be ultimately big, because we all know the even for NVIDIA GPUs, they will try to limit the size of the whole chip, because as the chip gets bigger and bigger, the power consumption, the heat and so on will degrade the performance of the chip. Yeah. But except that there's no more other restrictions of our in-memory computer core, because our in-memory computer core is based on pure logic. It's not a special memory cells. Yeah.
Great, sounds good. Chetan?
Yeah, sorry, Wei, I couldn't write my question
Don't worry,
box.
don't worry.
Yeah,
I'm glad we're
right.
getting a lot of questions. Yeah.
Yeah, thanks, Dr. Liu, for a nice presentation. I have a few questions. So one, which you mentioned for the time series data, you might use some kind of filter banks or MFCC, right, in analog domain. Since it's analog, there would be some artifacts, right, mismatch and temperatures, right, and that would affect your feature set which you are using to train your model. So how would you compensate that artifacts for your accuracy?
I think that the truth is that after the neural network gets developed, a neural network doesn't need so high resolution input as well as so high resolution computing units. That's
right. That's right. But because of the temperature, your feature itself would change, right?
I think there is always a misunderstanding about like analog circuit. It's it will change, but it will change. How to say? For example, if you design an ADC, the part that will change, the part that is really volatile to temperature to process, it's the least significant bits. The most significant bits will the chance that it changes is really low. If you really want to say it changes, if we look at a digital transistor, it also changes. It's just the chance that it changes is low, and yeah, it's the same.
Okay, so regarding another question regarding your computation, right? CIM chip. Yeah. So you're saying it's more like an in-memory computing where data flow is in digital and the computation is in SRAM, right? Is that right? My understanding?
Yeah, data flows in a digital. Data flows at the digital representation, but the computing is analog.
Is in memory, right? So now the question is how you are taking care of this sparsity, data sparsity, and weight sparsity for this kind of architecture.
Yeah, for what I mean is so in terms of sparsity, you can if your network is really sparse, then you can make different make the size of the slice, because our group of memory cells, computing cells, you can fine grain them into different size. If you're so it's basically like depending on the normal use cases of your chip, because right now we don't do like really general purpose chip that can do everything, because then it cannot be so efficient. But if you so when we design our chips, we try to make it semi application specific. Then it means so for example, if for tiny machine learning, if the networks are really sparse and so on, then we can actually put the slice, smaller, that includes less memory cells. Do you get what I mean? Yeah.
That's all right. So just last question is, since it's in memory computing, I'm assuming in SRAM you might be storing the weights, right?
Sorry?
In the SRAM, you might be storing the weights, right? And your data is flowing from...
Our approach is weight stationary, yeah.
Weight stationary, okay. And it's not possible to extend to output stationary or mix of both. Is that right?
I mean, it's possible to do that, but we compared different approaches. We think weight stationary is the best for our architecture and is the best for our targeted application. Yeah.
Sure. All right. Thank you.
Yeah.
Thank you, Wei. Thank you, Dr. Liu. Yeah.
Sure. I think we have one last question from the audience, Dr. Hongjie. So the question is, what kind of software tool do you use for model training as you are using a mixed architecture?
So the training part is the same. We also use TensorFlow or PyTorch. But to map the trained network onto our chip, Reexen will offer a development kit. So yeah, intermediate layer to transfer the trained network from popular frameworks to our chip. Yeah.
Okay. Yeah. Thank you. Thank you very much for the presentation.
Thanks.
So with that, I think we can wrap up all the technical sessions for this morning. Thank you for all the audience who stayed on with us. Hope you all learned something new. I also want to extend our gratitude to all the tinyML strategic sponsors who made this event possible. At the executive sponsorship level, we have ARM, my old employer, who provides the software and the hardware foundation, tinyML. Edge Impulse is the tinyML platform for all developers. Qualcomm advances AI research to make efficient AI ubiquitous. Sentient offers end-to-end deep learning solutions for tinyML and Edge AI. At the Platinum sponsorship level, we have Reality AI adds advanced sensing to your product with Edge AI and tinyML. Renesas, who has big ideas for every space. With our golden sponsors, Latent AI develops adaptive AI for the intelligent edge. Maxim Integrated, who is now part of Analog Devices, enables edge intelligence. Seed Studio, they are the IoT hardware enabler. tinyML builds smart IoT sensor devices from data. SynSense builds sensing and inference hardware for ultra-low power devices. We will have some special partner sessions in the next few days, led by the sponsors we just introduced. At the silver sponsors level, we have Aeon Devices, Deep Light, AMSA Vision Sense, GreenWaves Technology, Gravity, HOTG, Imagine Mob, Kixel, Reexen, and SAP.